Assalamualaikum warahmatullahi wabarakatuh. This is video for chapter 6, bonding in complex ion. So the learning outcome of this chapter, first you should be able to apply the knowledge of electrons configurations of the transition metals and ligand structures to determine the hybridizations of coordination compounds. And the second learning outcome is to conduct, observe and report the scientific investigations in selected areas of inorganic and coordination chemistry. For the content for this chapter, first we were going to learn about valence bond theory, which is including sp3, dsp2, sp3d2 and d2sp3. And the next we also going to learn about crystal film theory in square planar, tetrahedrals and octahedral complexes. And next we're going to learn about the magnetisms and also the color of the coordination compound. First, we look into the bonding in complex ion. So you need to know that the bonding in complex ion, including the metal, two ligand bonds, form when a field orbital of a ligand overlap with an empty hybrid orbital on the central metal atoms. So as you can see here, for metal, they actually contribute a vacant metal hybrid atomic orbital, which is usually the d orbital, while the ligand will contribute a pair of electron to be overlapped in order to form a coordinate covalent bonds, or known as dative bond. The molecular geometry is predicted using VSE PR. So when we're going to do the bonding in complex ions, so we need to know the characteristic of the ligand. So the strong field ligand will cause the d electrons in a metal to be paired up, whereas the weak field ligand will not cause the d electrons to be paired up. So this is the list of common ligands used. The strong ligands including CN and O2, CO, ethylene diamine, ammonium. And the weak ligand like iodide, bromide chloride and fluoride. So now we're going to look into sp3 valence bond theory first. For sp3, or known as outer shell hybridizations, it's for 4 coordinate compounds. So if you have 4 coordinate compounds, so it either can be sp3 or dsp2. So if you have sp3 VAT or valence bond theory, sp3 hybridizations, it means that your punya complex is outer shell hybridization, or they can have a tetrahedral complexes molecular geometry. Examples here, consider COCl4 2-. So the first step is you need to know the oxidation number of cobalt. Why? Because we need to know how many electrons are actually in d orbital of cobalt. So you calculate here, then you know that the cobalt is in oxidation number is positive 2. So from there you need to know the electron configuration for cobalt and cobalt 2+. So from here you know that we have 7 electrons in d orbital of cobalt. So you need to write. So this is the first step, second step, and then the third step. And in this step, you need to actually look out into what type of ligand used in this complex. As you can see here, since the ligand is chloride, which is a weak ligand, so the 3d or the electrons in d orbitals do not pair up. So this is the original arrangement of the electrons, and then since you need to have 4 empty orbital for 4 coordinate compound, so you need to use a 4s and 4p empty orbital. 1, 2, 3, 4, you hybrid. And then you get, this is the new arrangement of valence bond theory for this complex, which is you have 3D and sp3. So this one, the empty orbital will be filled up with electrons from the ligand. So this is the 4th step in order to write down on the valence bond theory for sp3 outer shell hybridization. If you have sp3 outer shell hybridization, it means that the complex should be in molecular geometrically tetrahedrals. Next. we're going to look into DsP2. DsP2 also known as inner shell hybridizations for 4-coordinate compound also. But if you have DsP2 hybridization, it means that the molecular geometry of this complex will be square planar. Okay, examples here, nickel and cyanide 4. First, you need to find out the oxidation number of nickel in order to get the electron configuration for nickel 2+. Okay, since we have an oxidation number of nickel in this complex is positive 2, so the electron configuration for nickel 2 positive is 3d8. So, you write down the electron configuration. Okay, this is a 3d orbital, 4empty, 4s and 4p orbital. And then, since the cyanide is a strong ligand from the list given before, it causes the electrons in the 3d orbital to pair up. Okay, so this one will be paired up here, so you get here. And then you get empty orbital in D, S and P. Since they are 4 ligands surrounded the central metal atom, so you hybrid 1D, 1S and 2P from here, and you hybrid and you get a DsP2 hybridizations for this complex. So you fill up this empty orbital with the electrons from the ligand. So for 4 coordinates, you need to know that you have sp3 and DsP2. And it depends on the number of D, how many electrons in a D, and also the ligand, strong or weak, in order to recognize if either it can be sp3 or tetrahedral complex or DsP2 known as square planar complex. If DsP3 known as outer shell hybridizations, is DsP2 is known as inner. So why is called as outer? Why this one is inner? As I can share here that when it say inner is because it hybrid the inner orbitals here from D orbital. Okay, compared to sp outer, they just hybrid the outer orbital. There is a difference between outer shell hybridization and inner shell hybridizations. Okay, next we're going to look into 6 coordinate compound, either sp3d2 or d2sp3. Both of these valence hybridization will cause the same molecular geometry, which is octahedrons. The difference between if sp3d2 is known as outer shell hybridization. Okay, so how to get the outer shell hybridization? The method is the same. First, okay, if you see you have 6 coordination numbers, so you know that it will become octahedral molecular geometry. But what type of hybridizations? So next, first you need to know the, of course, the oxidation number of the metal. So from here you calculate, you get the positive 3. So next you need to know, the electron configuration for the iron 3+, so you get 365. And then same goes, okay, macam tadi juga. So you need to draw the orbital diagram for iron 3+. So you know you got 3D, dia ada 5 electron, 1, 2, 3, 4, 5. And since that the ligand is water, which is a weak field ligand, so the electron is no need to pair up. So you need to just get a 6 empty orbital from 4s, 4p and 4d to be hybridized, and you get the sp3d2 hybridizations, and also known as outer shell because you hybrid the outer shell. Okay, if you have 6 coordination number, okay, of course 6 coordination number, the geometry is a molecular octahedral, but what the difference is here, we have D2sp3 known as inner shell hybridization. Okay, the method is the same. Okay, the first one you need to know the oxidation number of the metals. Okay, sorry, this is actually Fe. So you get 3+. Okay, so the second one, electron configuration for Fe3+ is 3d5. Okay, now you write the orbital diagram for iron 3+. Since that you know that the Cn is a strong ligand, so the electron in the 3D will be paired up. So this one will be paired up here. This one akan ke sini. this one akan pair up dekat sini, and the last one akan masuk ke orbital yang number 3. So now you have 2d empty orbital, 4s and 4p. Since there are 6 ligands surrounded, so you hybrid these 6 empty orbital, so you get D2sp3, and known as the inertial hybridization. Why? Because you starting to hybrid from the inner orbital 3d. Next, that is for valence bond theory. Next is for crystal field theory. Okay. In crystal field theory, it explains that the bonding on complex ions purely in terms of electrostatic forces. They have 2 types of electronic interaction involved. First one is the attraction between positive metal ion and negatively charged ligand, and the second one because of electrostatic repulsion between the lone pair on the ligands and also the electrons in the orbital of the metal. So is the crystal field theory for octahedral. So this is all the orbital for d orbital. So first we look into the crystal field theory for octahedral, which is 6 coordinate compound. The central metal atom will be surrounded by 6 electron lone pair. So all 5d orbitals will be experienced the electrostatic repulsions. So the magnitude of repulsion depends on the orientation of d orbital involved. So for dx squared, y squared, and dz squared, the loops point towards where the lone pair located. Thus, it will experience the greater lone pair d orbital electron repulsion, and they will be higher in energy. Thus, 5d orbitals are split into 2 sets of energy level, which is for T2G set of orbital, which is in lower energy for dxz, dyz, and dxy, while EG set of orbital will in higher energy dz squared, dx squared, and y squared. So here, so this is how you draw the diagram, schematic diagram for octahedral crystal field theory. So you have energy here. So this is a d orbital. Okay, because of the interaction between the metals, ion, and also the electrons from the ligand. So it is separated. So the orbital for dsy, dyz, and dsz will be in the lower energy T2G, while the dz squared, dx squared, y squared will be in higher energy EG. The energy difference between these 2 sets of d orbital in the metal atoms when the ligand are present, and this kind of crystal field theories actually have direct effect on the color and magnetic properties of the complex ion. So next we're going to look into the tetrahedral complex. For tetrahedral means that the central metal atom surrounded by 4 electrons lone pair. So the d orbital of tetrahedral complex also split into 2 groups, mean dxy, dyz, and dxz. Orbital is actually point in the direction of the ligands. So they will be higher in energy than the degenerate orbital of the free metal atom or ion. Okay, sebabkan this orbital, okay, directions of the ligand, it mean orbital point in the direction of ligand. So ligand masuk dekat orbital itu. That's why they have higher energy compared to the free metal atoms. Okay, and for dz squared and dx squared, y squared, since that the orbital points between the ligand, that they are lower in energy. So they have 2 sets of energy level, which is T2G, which is the higher energy is for dxyz, dyz, and dxy, while EG set for orbital in the lower in energy is dz squared, dx squared, y squared. So the difference for tetrahedral and orbital is that they just terbalik saja. Okay, kalau untuk octahedral, 3 this one dekat bawah EG, dx squared, y squared dengan dz squared kat atas 2G. Tapi for tetrahedral dia terbalik. Okay, and for scale planar, since there are 4 ligand as well, same goes to the tetrahedral, but the difference is that the electron of ligand are only attracted to the plane. So there are 4 different energy level for the square planar. So the lower energy is dz, yz, okay, followed by dz squared, dxy, and the higher energy is for orbital dx squared y squared.